Hello, I'm Patty Simpson with Simpson Math. In this video, we're just going to introduce inverse functions. So first, let me just explain to you what an inverse function is. So if we have some function and we input a value, say we input, I always think of it like Coke machines. If I input my money into the Coke machine, so here's my money into the Coke machine, I put the money in, and I push a button, and out comes Dr. Pepper. So out comes my can of Dr. Pepper. Then, what an inverse function does is, if I take that can of Dr. Pepper and put it in that inverse function, then out would come my money. So the inverse function just undoes what the original function did. So my input and my output of my original function swaps places and becomes the input and the output. My output becomes my input, and my input becomes my output in my inverse function. Or if we think about it with actual functions, let me just show you an example. So here, my original function is 6x minus 1. So if I input some value in there, say 3. If I input the 3 in for x, well, I get 6 times 3 minus 1 gives me 18 minus 1, and out comes 17. This function is going to undo what this function did. In other words, I'm going to put in the 17, and out should come 3 if they're inverses of one another. So here I have x plus 1 over 6. I'm going to input that 17 in for the x. So I have 17 plus 1 over 6. Add 17 plus 1 and you get 18 divided by 6. And out comes 3. Notice that it did undo what the original did. So in inverse functions, my x values and my y values swap places. So here my x was 3 and my y was 17, but in the inverse function, my x was 17 and my y was 3. So let's graph inverse function. I'm going to graph the inverse of this particular function. Another characteristic of inverse functions are of functions, in order for them to be able to have an inverse, is they have to be one-to-one. In other words, they have to pass the horizontal line test. Remember when we talked about functions, we said a function had to pass the vertical line test, that every input had to have a unique output. Well, in order for that function to have an inverse, every output then must have a unique input. In other words, it has to be one-to-one, or we should be able to draw a horizontal line anywhere on here, and it only hit one time. Notice this one does. I can draw a horizontal line anywhere there, and I'm only going to hit the graph in one place. Think about our parents for a minute. Our linear functions are one-to-one. I can draw a horizontal line, and I'm only going to hit the graph once. But look at my quadratic functions. If I draw a horizontal line there, I hit it twice. So the quadratic function, I can't find an inverse for unless I restrict the domain of it, unless I do something where I just talk about it for part of the quadratic function. So in order to be able to find the inverse, it has to pass that horizontal line test. It has to be one-to-one. This one does pass that horizontal line test. I can find its inverse. So let's find its inverse. What I'm going to do is just label the points on here. So here, this point is at 1, 2, 3, 4. So -4, -4. There's another point at -3, -1. Here at 0, 0, and at 1, 3. Now the inverse of this function, my inputs and my outputs just switch places. My x values and my y values are just going to swap. So on my inverse function, if I take and swap those, I'm still going to have a point at -4, -4. This one though, when I switch the places, I'm going to have a point at -1, -3. Here, I switch the places, I still have a point at 0, 0. But this last one, when I switch the places, I have a point at 3, 1. So the points on my inverse functions are as follows. Let me then graph those points. -4, -4, -1, -3, 0, 0, and 3, 1. Connect the points. And this purple one is the inverse of the black. Those two are inverses of one another. Notice that if I draw a line right here where y equals x, that parent linear function, that this is reflected over that line. That if I folded on this line, that point would go here. This point would go there. That's always true of inverses as well. They're always symmetric about that y equals x line. So some characteristics of an inverse function. Our inputs and our outputs just switch places. Our x's and our y's just swap. The graphs are symmetric about that y equals x line. And the domain and the range, since our x's and our y's swap places, our domain and our range switch places. So there's some basics about inverse functions. In the next video, we'll mathematically define an inverse function. Math made simple, it's Simpson Math. Thanks for watching.